Yesterday, we made the transition from pure circular motion to that application of mostly circular motion involving heavenly motion. We looked at a little bit of a historical development of the current ideas that we have of the motion of planets, starting with about 2,500 years ago, Aristotle. Aristotle had what we call the geocentric theory or the geocentric model of the universe. Geo means earth, centric means centered. The earth-centered theory. The earth is the center of the universe, and everything revolves around the earth. We talked about this yesterday. We said that although that seems kind of silly now, we all know that the earth is not the center of the universe. In fact, the earth revolves around the sun. If we just looked up into the sky, we might think the same thing. We might think that the sun revolves around the earth as well. We know that the earth isn't the center of the universe because somebody told us. So it's not as far off as it might seem. Fast forward a couple thousand years to Copernicus. The heliocentric. Centric means centered. Helio means sun. The sun-centered theory. All the planets, including the Earth, and that's the important one, really, right? All the planets, including the Earth, revolve around the sun. And then finally, not finally, almost finally, we zoom forward about 50 years to Tycho Brahe. He's the P guy, remember? Okay, the gold nose and P guy. Late 1500s, he observed things. He measured angles, he measured distances, he measured times, and so on and so on and so on, and then he died. But his assistant, Johann Kepler, took that data and did something with it. Johann Kepler came up with 3 laws that describe the motion of the planets. Not why they do what they do, but rather how they do what they do. Now, those 3 laws consisted of the following. 1, the law of the elliptical orbits. This one says that the sun is in a certain place. Here's the sun. The Earth will travel around the sun in an elliptical path such that the sun is at one of the focal points of the ellipse. So the ellipse might look like this, but the ellipse might look like this as well. The sun is at exactly the same position, but the ellipse is different. You've got the sun at one of the 2 focal points, and the ellipse that goes around, or the path of the Earth, or whatever other planet it is, that goes around it in that elliptical path. We've got it drawn here with the sun in 2 positions. Of course, the sun isn't in 2 positions. It's either at position 1 or it's at position 2. It's not going to move back and forth. It doesn't decide where to go based on the path of the Earth. Rather, the Earth decides where to go based on which focal point which focal point the sun is at. Secondly, we talked about the law of equal areas. The law of equal areas says that you got the sun right here in the middle. Not in the middle, but at one of the focal points. And then you've got the Earth over here. We'll call it at position 1. The Earth has, if the Earth and the sun have an imaginary line joining them, during a certain amount of time that we'll call T1, the Earth will sweep out a certain area that we call A1. So this area in here called A1. Now fast forward 6 months, the Earth is over here in position 3. A line joining the sun to the Earth at position 3 will sweep out a certain area until the Earth gets to position 4. Now, if that time, T2, is the same as time 1, maybe it's a month and a month, 6 days and 6 days, 38 days and 38 days, whatever it is. If T1 equals T2, then the area swept out in both cases is going to be the same. So if T1 equals T2, then A1 equals A2. So what? Well, it has a pretty big implication for the motion of the Earth and other planets. You can see that over here on the left-hand side, the Earth travels a certain distance in a certain amount of time. Over here on the right side, the Earth travels a much shorter distance in the same amount of time. That means if the time is the same and the distance is different, then the Earth is changing speed as it goes around the sun. Where's it going fastest? When it's further away from the sun or when it's closer to the sun? When is it going the fastest? When it's closer to the sun. It travels more distance in the same amount of time. So the Earth is going around the sun, and all other planets are going around the sun for that matter like this. Speeds up, slows down. Starts speeding up, Start slowing down again. It doesn't take that funny little path that I just showed you right there, like this. Just takes this nice ellipse, speed up, slow down. Speed up, slow down, and so on. It's not quite as exaggerated as we've illustrated here. Okay, the ellipse is much closer to being a circle, therefore the speed isn't nearly as different as I show you here. Okay, but the idea is there. The speed changes. The ellipse is there as opposed to a circle. If T1 equals T2, then A1 equals A2. Finally, the law of periods, and this might have been the hardest one to understand. If you've got, let's say, the sun, if you've got, let's say, Saturn, could be any other planet or anything else that has something revolving around it. The sun has a certain constant associated with it called Kepler's constant. Kepler's constant for the sun is equal to t squared over r cubed. What's t? Well, t is the period of revolution. The period of revolution of what? Well, it could be the period of revolution of the Earth, the radius of revolution of the Earth. Or it could be, for that matter, the period of revolution of Mars divided by the radius of revolution of Mars cubed. It could be, for that matter, the square of the period of revolution for Jupiter divided by the cube of the radius of revolution for Jupiter. We're saying Kepler's constant for the sun is determined by T and R for anything that's revolving around it. It doesn't matter. The ratio of T squared to R cubed for anything revolving around the sun is the same. Now, let's look at Saturn. Kepler's constant for Saturn is different than Kepler's constant for the sun. T squared over R cubed for one of the moons orbiting around Saturn. T squared over R cubed for another moon orbiting around Saturn. Now, these two Kepler's constants are the same. These three Kepler's constants are the same, but these two Kepler's constants are not the same. So what use is this to us? So what? Well, this allows us to find properties of planets and orbiting objects from properties of other orbiting objects. So for instance, if we know something about the Earth, we can find Kepler's constant for the sun. And then we can work backwards, knowing Kepler's constant for the sun, to find the radius of Jupiter, or to find the period of Jupiter, or something else. Okay, knowing the period and the radius of revolution of moon number 1 for Saturn will allow us to determine Kepler's constant for Saturn. Then we can use that value to measure some of the properties of moon number 2 going around Saturn. That makes sense? So the law of periods talks about this relationship between the period of revolution of an object going around another object and its average radius of revolution. All right, it's all good. We've just determined how the Earth and other planets revolve around the sun. But why? Why do they revolve around the sun? We experience, or planets experience, this motion around the sun in an elliptical path such that the sun is at one of the focal points, such that the square of the period is proportional to the average radius of revolution, such that the areas are the same, swept out by a line are the same if the times are the same. We experience that motion because of a force called gravity. Gravity is a force that exists between any two objects with mass, between you and your neighbor. It's a small force because you're light and your neighbor is light. You experience a force between you and the Earth. That's a bigger force because although you're light, the Earth is heavy. Between the Earth and the sun, now we're talking about massive objects. The force of gravity between planets and suns and heavenly objects, that's a big force. That's a big force because we're dealing with such small masses. Newton, as the story goes, he's sitting under a tree. You guys have all heard this probably, right? Sitting under a tree, the apple falls on his head, and all of a sudden he has this eureka moment. He discovers gravity. when the apple hits him in the head. He figures the apple's got mass. The earth has mass. The apple fell down because it's attracted to the earth because of the mass. That must be why the earth is attracted to the sun, because they both have mass. But the earth has more mass, so it's attracted to the sun even more than the apple is attracted to the earth. Nobody really knows if that actually happened or not. We think that it probably didn't happen, actually. But in the end, Newton still came up with this law that described this force of gravity that acts between two objects, between any two objects with mass, including the apple and the ground, between you and your partner, between the earth and the sun. How do we describe mathematically this law that describes the force of gravity between two objects with mass, whether they be you and your neighbor or whether they be the earth and the sun? What are those two absolute values? Whoops. Just gave that away, didn't I? What do those two vertical lines mean? We talked about this with friction. It's absolute value, right? The absolute value meaning that there is a direction associated with this, but the equation won't tell me what it is. That's okay. We're talking about a force of gravity. We know it's an attractive force. Just like we know that the centripetal force will be toward the center. We already know the direction of the force. It's an attractive force. You're attracted to the ground. The apple is attracted to the ground. The earth is attracted to the sun. It's equal to g, which is a constant. It's a constant that we call the gravitational constant. We'll tell you about the details of that in a moment. Times m1 times m2, the mass of the earth, the mass of the sun, the mass of the apple, the mass of the earth, whatever two masses you're dealing with, in whatever order you want to list them, divided by r squared. R, not a radius necessarily. R is a distance between the two objects, the centers of the two objects. If you're talking about the earth and the sun, yeah, it's the radius of the earth's orbit around the sun. If you're talking about the space shuttle orbiting around the earth, yeah, then r is the orbital radius of the space shuttle orbiting around the earth. But if you're talking about you and your neighbor, then r would be the distance between you and your neighbor, a meter and a half, 2 meters, whatever the case may be. It's not a radius, it's just a distance that separates the two objects. G is a constant, we call it the gravitational constant. I told you when I was on our little aside about Einstein's theory of relativity, I told you that gravity is actually a relatively small force in the grand scheme of things. Well, here's the value of the constant. 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. It tells you it's a pretty small force, right? The number that you have to multiply by m1 and m2 and r squared is 10 to the minus 11. It's a small constant. It gives you a small force, unless you have giant masses. M1 and M2 are the masses, and that's going to be measured in kilograms. In R, not radius, or not always radius at least, it's the separation distance. And that separation distance is, of course, measured in meters. That constant, the good news is on your data sheet, including the units. If that messes you up at all, you can always find them on your data sheet, the numbers on your data sheet as well. Let's do a quick little example before we do our real example. I asked you a few minutes ago to look at your neighbor and talk to your neighbor and say a few words to your neighbor and basically to establish that there's a force of gravity acting between you and your neighbor. Let's figure out roughly what that force would be. Okay, let's figure out what the force of gravity would be between you and the person sitting beside you. Well, F is equal to big G times M1 times M2 over R squared. Always make sure you make that a big G, because little g is 9.81. That's a big difference, 9.81 versus 6.67 times 10 to the minus 11. Big G is 6.67. M1, it's the mass of you. Let's say you're 50 kilograms. The person sitting beside you is 70 kilograms. And we divide that by the distance that separates you. For some of you, it's a meter and a half, 2 meters. Let's go with 1 meter. The closer you are, the bigger the force of gravity that will exist. So we'll go with a smaller number. Let's calculate this now. We get 6.67 times 10 to the minus 11 times 50 times 70. We divide that by 1 squared, and we end up getting a force of 2.3 times 10 to the minus 7 newtons. Is that a big force? Oh, it's a tiny force. And that's why you don't feel that force of gravity between two people. Okay, let's just 1 second here. If you substitute the mass of the Earth for this, which is 5.98 times 10 to the 24 kilograms, then all of a sudden you can see that that force is going to become way, way bigger. That's why we notice it between you and the Earth. All right, we'll pick up there on Monday, okay?